Thank you everybody for joining and welcome to our crowd's webinar on quantum technologies and how it's going to affect our future. Our crowd is the leading equity crowdfunding platform which invests in innovative technologies. One of these companies are QuantLR, which you'll hear about momentarily. I'm Stav Erez. I'm a partner at Labs02. Labs02 are our crowd's seed fund stage and incubator. We invest in deep tech companies. And I would like to welcome the speakers for today. Please meet Hagai Eisenberg. He's an associate professor at the Rakach Institute of Physics at the Hebrew University of Jerusalem and the co-founder and chief scientist officer at QuantLR. Hagai, can you introduce yourself?
Hello and welcome everybody. So as I was introduced, my name is Hagai Eisenberg. I'm a professor of physics at the Hebrew University. I have this position for the last 15 years. I'm an experimentalist working in the field of quantum optics, which is the combination of quantum technology and light, which is very relevant to the company that our company that Stav mentioned, QuantLR. And before that, I was studying in various places like the Technion, the Weizmann Institute, and the UC Santa Barbara. That's my history.
Thank you, Hagai. And please meet Dr. Tal David, head of the Israel National Quantum Initiative, holding a PhD in quantum sensing with cold atoms. Tal, can you tell us a bit about yourself?
Yeah, thank you for having me today here. So I'm a quantum physicist. I did my PhD at Ben Gurion University studying cold atom physics and metrology. Then I moved to the industry to a laser technology startup. Then I formed a group doing quantum magnetic sensing. Then I joined the government. And in the last year, after forming the Israel National Quantum Initiative, I'm heading that on behalf of several R&D agencies, and we'll talk about it a little later.
Thank you, Tal. Okay, Hagai, can you please just give us a background about what it is? What is it, quantum technology? What does it mean?
Okay, so quantum mechanics, the theory of quantum theory is here already for almost 100 years, and it already affects our life in every day through what we call today the first quantum technology revolution. You are all familiar with the invention of the transistor and the laser in the 1950s and 1960s. And these two technologies, together with others, but these are the main ones, they are the initiators of what we call today the information revolution, the age of information, where everything is information, everything is based on information, information is money. And this is what let us compute, transfer the information from place to place. And here is just a picture of a large data center where transistors are the basic of all the servers inside it, and lasers are what used to transfer information from place to place. Now, if we check what is common to all of these technologies in the age of information, we see something in common. In every technique, we store information, manipulate information, transfer information. Like there are a few examples here, like hard disks that, or disk on keys that store information, computers that process information, or the optical fiber backbone for optical communication, which transfers information from point to point. What is common to all of these is that the information there obeys classical physics. Quantum mechanics has nothing, quantum physics has nothing to do with this. And when we ask ourselves, what will happen if we store information in quantum systems, such as trapped ions, all kinds of structures in diamonds, superconducting qubits, which are called today, or all kinds of optical realizations like the photon, which is a bit of light, which obeys quantum theory. What will happen to the information, and what can we do with information when it is stored in these quantum systems? And all all this led to a second revolution, which we call today the second quantum technology revolution, which sits on three pillars, we call them. One of them is about processing information. These are machines that we call quantum computers, machines where the information inside them is stored in quantum systems. And as we saw in the previous slides, there are many realizations, but the most common one today used by Google and IBM and others are these superconducting devices. We discovered that we can create computers that can solve problems that we cannot solve on traditional computers. And then we ask, what will happen if we transfer information using these qubits, these quantum bits, these quantum bits of information? And the answer is that we can get to unprecedented level of security, which we will talk later. And then we also say what if our sensing machinery that sense the environment, like what we need for autonomous cars to sense, to map the surrounding and to feel whether there are obstacles or to read signs. And there are many other examples. So all this sensing equipment, what will happen if we treat the information that it reads from the environment using quantum information? And we discover that we can do new things. We can sense with better sensitivity. We can build smaller sensing devices and so on. So we are convinced that this second quantum technology revolution is already starting to affect our lives, as we will discover in the next few minutes, and it's going to tremendously change our life, as we are going to discuss later. Thanks.
Thank you, Hagai. Tal, if you had anything to add, and in addition, I would like to ask you whether there are quantum technologies that we're already using them today, if it already affects us today.
Yes, so if we look at this plot, which is very qualitative, it's not quantitative in any sort of way, we can see these three vectors that Hagai was mentioning in a sort of mapping of where they are in the level of technological maturity over time. So the most mature vector is the sensing vector. We've had quantum devices sensing stuff for quite some time, starting with atomic clocks that measure time or frequency very, very precisely. The reason that quantum sensors are so accurate or precise comes from the fact that we know to control these quantum systems and isolate them from the environment very well. And because of the discrete nature of quantum physics, this leads to a possibility to measure the structure of, for example, these trapped ions or atoms that were mentioned before in the most precise way in nature. So for example, atomic clocks are now used to give timestamps in the financial markets in order to have extreme resolution in the timing of transactions. They are used in smart electrical grids to synchronize between power coming from different power plants. They are used in communication synchronization. They are used in navigation, like the GPS system, which all the satellites have atomic clocks in them. But it's not only atomic clocks and time and frequency, it's also, for example, magnetic sensors, quantum magnetic sensors that are used in geophysical exploration, for example, to search for underground deposits of oil or gas or other minerals. They are used in, quantum sensors are starting to get used in navigation of extreme precision. And so on. The other two vectors are not so far behind, but they are a little bit less mature. Quantum communication is something that we'll talk about a lot in the next few minutes, is growing very rapidly. And quantum computing is something that is very challenging, but it's ramping up at a tremendous pace, and the impact will be amazing, changing really the very basics from our lives. It's not only about code breaking, which is the buzzword that everybody is talking about, but even before that, we will see quantum computing used for optimization, for developing new materials, for developing new drugs. Today, developing a drug is a decade-long process with a $1 billion investment, and quantum computing will be able to assist in narrowing this down to a much more practical way. And then we have quantum machine learning and database sorting and so on, and also code breaking in the farther future.
And as you're heading the Israel National Quantum Initiative, are you focusing on all three verticals or specifically on one that is closer today?
Right, so, you know, we Israeli, we can say that we focus on just a few things, but we turn up to be focusing on everything at the end, right? So we'll talk about the national initiative in a few minutes, but we have a few components of the initiative that are, you know, lateral, that have no preferences, right? You could see that here. So, for example, we invest in direct academic research or in developing human capital by supporting new faculty in academia, by supporting grants for postdocs or PhD students who are excellent, by adapting the training, both in academia and in industry, to be more quantum oriented, and pushing the engineering training to be more quantum oriented. So all of the things do not have a real preference. But apart from that, we have three focus areas, one in quantum sensing, one in quantum communication or quantum key distribution, which is ramping up much faster than we anticipated before, and also in quantum computing. And I'll elaborate more on that in a few minutes.
Okay. Hagai, any other applications of quantum technologies you'd like to address?
So I'm postponing unless you want me to do it now, talking about communication.
You want to talk about a bit about communication, we'll later talk about really the risks, but tell us a bit about quantum communication.
Okay, we have a slide later on, which we first have to introduce what's going on. Why do we need? What is the problem that needs a solution? So.
Okay, I thought that you're going to give like a bit of a background about quantum communication. So let's go back to the risks a bit later. So Tal, I'm happy to hear we talked a bit about the present, and I'm more interested in hearing a bit more about the future, how quantum technologies are going to impact our future, how it's going to change our future.
All right, so we can maybe give a few examples. Talking about quantum computing, you can imagine that instead of doing some computation or algorithm in a sequential way, you could do everything at once or in a very small amount of steps. So for example, a very famous example is if I give you a phone book and I tell you a number in that phone book, and I ask you to find out who this number belongs to. So you and the classical computers more or less go one by one to search for the right number, because the phone book is oriented in an opposite way to how I phrase the question. In quantum computing, there is an important principle from quantum theory that is called the quantum superposition, where we can take the bits of the computer, or in the quantum computer, the qubits, and we put them in a mix of a state which is both in a zero logical state and a one logical state at the same time. We can do that at the level of one bit, and we can do that at the level of the whole processor. And this gives us the ability to do, instead of a lot of sequential steps, we're doing a few parallel steps in our algorithm, increasing the efficiency or the speed of the calculation, and thus allowing us to solve problems that are very complicated to solve. So for example, there was a preliminary example from work that was done by Volkswagen, the car company, together with a quantum simulating company called D-Wave from Canada about a year ago, where they used the quantum simulator or quantum computer of that company in order to run quantum algorithms for the optimization of transportation within cities. You know, that you will have more green lights and less traffic. I think that has a tremendous economical impact. And they have shown, even in the small quantum computers or simulators that we have today, they have shown a 1 billion increase in the efficiency of the calculation or the speed of the calculation relative to how it's done today. So you can think about such efficiency impacting the time that you lose every day sitting in your car in traffic. I think this is an example that everybody here knows about, and you can take it from there to other optimization problems, like I mentioned before, about drug development, material development, and information processing in general. As we'll see later on, quantum computers may also be used in the future for code breaking. And in order to combat with that, we will talk about quantum communication or quantum key distribution as a way to have an ultimately secure communication, which is something that is also very relevant even today, because every transaction that we buy on eBay or AliExpress, every email that we send, every transaction that we do with the bank, everything is encrypted, and this encryption is always at risk. So we'll talk about that. And I think that this is a few examples of how we see the field developing today and to the future.
Okay, just to remind everyone, we have at the bottom of your screen a Q&A section. So after we're done with the panel, you can already start, by the way, writing questions. So just press on the Q&A and feel free to ask us whatever you want to know about quantum technologies. So Tal, I'm gonna stay with you for a second here. I was wondering, what is the role of the government in developing quantum technologies or infrastructure?
Right. So if you look at the world today, you see that there are many national initiatives. They are quite big. So you could see it from the US, Canada, the European Union. Germany has just declared about a month ago that as part of their push to take the market out of the COVID-19 crisis, apart from the social network that they've been investing, they will invest also in technological vectors, and quantum technology is one of them. So the world governments understand that this area is something that will create more economy, more jobs, more revenues in the future. The Chinese are very strong in that. And also you see big multinational corporations investing, like Hagai mentioned before, IBM, Intel, Microsoft, and so on. The reason that governments are important is because although we passed through and said that we can control the quantum systems very nicely and isolate them from the environment, it's not such an easy thing to do. The technological challenges are very big and very substantial to realize these machines. So quantum sensors, they are relatively easier to manufacture, and that's why the maturity there is stronger. Quantum computers are much, much more difficult to realize that they will work very well without noise and so on. And because of that, there is a need for governments to push this forward, because you need massive investments to do that. You need the investments not only in R&D projects. You need to start from the education, the academy, the research, and then slowly build towards applications and projects and services. So the roles of governments all around the world is to push this as fast as you can and generate the advantage for each country, okay? So if we move to the Israeli National Quantum Initiative, this is a joint venture of all the leading R&D agencies in Israel. And this is the Council of Higher Education, which is pushing the academy forward. This is the Innovation Authority and the Ministry of Economics that are pushing Israeli industry. The Ministry of Defense is involved, Ministry of Science, and of course the Ministry of Finance. We have approved in the last year the program, which is at about 1.25 billion shekels, which is roughly $360 million, although the dollar is now dropping very heavily, so maybe the number is a little bit higher in dollar terms. And the program is supposed to take this money is supposed to serve for 5 years, the first 5 years as we look at it, because this is a long-term approach, and we take the assumption that it will continue further on. The biggest challenge that we have identified in Israel is that the community is very good. If you look at number of ERC grants, number of scientific citations, the level of performance of the industry. It's good. The community is also young, but it's a small community, okay? And for that reason, the biggest challenge is to enlarge the community and have a wide basis to build on for the further future. So we have defined all of these components that you see on the screen, starting from direct academic research, starting for taking care of the people to enlarge the amount of people in the system, both in academia and in industry. As we've briefly discussed before, we will also have a huge investment in physical infrastructure, fabrication facilities, characterization facilities oriented to quantum technology. We have some money to collaborate with partners internationally. And the idea here is not to replace all the regular platforms for international collaboration, but just to push them a bit towards quantum. And also, beyond all of these lateral components, as I said before, we have a few focus areas. One of them is quantum sensing, where we have, for a few years now, substantiated industry already working. Some of it is also selling already, and some of it is close to be entering the market, and we're going to put them in main projects in quantum sensing. So for example, we have initiated already, just exactly 1 year ago, in September 1 year ago, we initiated a consortium that has a few industries, a few academias working together on quantum sensing for better clocks, better magnetic sensors, gravitational sensor, and so on. Second focus area is in quantum key distribution or quantum communication. Here we thought, when we formed the national initiative, we thought this is no industry in Israel, this is only research, but things are moving very, very fast. We see more and more industry going into QKD, and we are about to initiate a similar industrial consortium also for quantum key distribution that will start later in this year. Finally, the third focus area, which we see on the left-hand side here, is quantum computing. The reason to define this as a focus area is very different from sensing, because we don't have industry really in quantum computing today in Israel. We have some very leading people in Israeli academia, but very few. So, on the other hand, we understand that the impact of quantum computing will be huge. So we have to be there. And when I say we have to be there, I don't mean that we are going tomorrow morning to beat IBM and Google. That's not the intention. We want to build enough critical mass of researchers working using both the state-of-the-art quantum computing that is available on the cloud today, but also invest in Israeli academia to generate more people in a faster time. And also what we call applied quantum computing, which is beyond academic level, to really put on the table in Israel a capability in quantum computer that will be relevant to talk with the world and serve as a basis for the farther future.
Amazing. Hagai, I'm moving to you. So we talked about the great advantages of the quantum computing. So a couple of questions. First of all, just are you related in any way to the Israeli Quantum National project? And second of all, we learned about the advantages. I would love to hear now about the risks involved.
Okay, so about your first question, the answer is yes, yes, and yes. In my many hats, I'm related in many ways to the initiative, either the academic hat, the QuantLR, the company, or through all kinds of initiatives that Tal is involved in. I am involved. I even said today that I think most of my academic grants are somehow related to Tal, maybe except for two. One of them is coming from the European Union, and the other one is just before Tal joined this thing. So otherwise, I'm very much related to and benefit from this initiative. Now about the reason for this party. So I'm continuing saying what Tal just said before about quantum computers. Quantum computers will have very specific strengths, and one of the most interesting is to be able to break what sits in the essence of all encryption codes today on the internet, and not just the internet, any way that we communicate. It doesn't even have to be just internet. We are talking about the way we remotely control critical infrastructure factories, the way we control our traffic lights, the way we keep our medical information, and any kind of communication is encrypted today. And quantum computers do threaten that. On top of that, there are few more reasons to be afraid before we try to calm you down. First of all is that even before the age of quantum computers, information is not completely secure. So if someone is very much engaged and wants to break into your system, eventually he will manage to do that just by what we call brute force, or just by waiting enough time, because it's true that things are secure, but are only secure for a specific term of time, and eventually it is possible to break. So many secrets, for example, even the secret key of your credit card, this is a secret you would like to keep for a few years and not change every month or every week. And there are many examples for that, like financial information and medical information, as I mentioned before. So information has to last in secrecy for many years. And again, the longer we keep information on the shelf, the less secure it is. There are attacks today of governments, mainly it's known, that are taking encrypted data. They cannot decrypt it, but they keep it for later. And maybe in 3 years, they will be able to decrypt it. On top of that, the last threat is that even if we say that, okay, data is secure today, but it will be only threatened in 5 or 10 years, it takes many, many years to accommodate, to adapt new technologies into the current communication infrastructure. And we have to start today to prepare for this, what is called the post-quantum era. And actually, the NSA already threatened companies with critical information to start to do it in 2016. So today we are already 4 years later, and it's clear to many organizations are already taking steps toward that. So what can we do to protect? The best solution is not to rely on computers and algorithms that decrypt the data, but to involve some physics in the way we create our secrets. And this is exactly the way we incorporate quantum information in our communication lines. We transmit single photons, which are these tiny quantum bits of light, and we put some information on top of them. And it was proven that no one can really break codes that are properly built on this infrastructure. As it was mentioned, it's called the jargon for the technologies, quantum key distribution, because what we do is actually we distribute keys for encryption in a safe way from place to place. And as I said, these are impossible to break. Now, I'm relying on something else that Tal mentioned. To incorporate this new technology is not easy. We define it, everyone is familiar with the term high-tech. This is a term I only learned in the last year. This technology will be categorized under deep tech. So what is the meaning of deep tech? This is high-tech, which you need many resources and integration of knowledge in order to incorporate it into the real world. But today, as also was mentioned, we are getting the grasp of it. We are able to materialize it and to build machines like that. And this is exactly the goal of our company, QuantLR, to make a good, useful, I'll define it in a moment, quantum communication, quantum encryption system based on these ideas. The main, if you want, mantra of our company is we identify that even though the technology, people started to think about it more than 30 years ago, people started to demonstrate it in academia about 20 years ago, it's only entering the market in the last 2 or 3 years in a real way. And the reason is, as I said, first of all, there's the barrier of deep tech, but on top of that, because all of the people that build the systems are coming out of universities, and I'm not, you know, I'm no different. But the point is that these systems are quite cumbersome to incorporate, and they are very expensive. And the goal of QuantLR is exactly to solve these two issues. Our statement is that we will reduce the cost of our first system tenfold of what exists today in the market, and then later on, after a year and a half or two, we will go further and further decrease the cost. And the second thing, we are not going to build full communication systems like others are doing, full machines which are the full size of a communication equipment, but we are going to build just a module that will be plugged as part of a standard communication manufacturers that build switches for the infrastructure of all the major carriers. And these manufacturers will incorporate at the beginning, just our module into their standard equipment, and just add this extra level of encryption, of quantum encryption, into their equipment. And later on, we don't even want to make the module. We just want to sell them the design, the reference design, and the software that runs on it. And they will build it, and they will sell it. We will just give the know-how, the knowledge, the deep tech. We will help them to pass this deep tech barrier. Now, currently, we are in a stage where we already have a full working demo in our labs. Here, our labs are located at the Hebrew University, co-located with my academic lab, and also supported by it with an agreement with the university. So we have a working demo. The demo is really advanced in many ways, which there's no time now to tell it. But what I can tell you is that we already took it out of the lab, put it on a real fiber in the ground that the university gave us, put it in a real communication room, and created keys over 3 kilometers of line. In the lab, we demonstrated it over 50 kilometers of fiber line, and we also incorporated our demo, just the demo, with the real product of another Israeli communication company. We just put our demo next to them. One communication cable connects our devices with theirs, and they just manage standard communication and encrypted it with quantum keys that we gave them. So currently, after the demo, we are looking to get to our first product, the module I just mentioned. Until now, we worked with the seed money that we got from Stav organization, Labs 02, and now we are currently on the platform of our crowd, and there's a money-raising process, which I think is still going on during August, so there's still a chance to be part of our product, of our next stage of evolvement.
If I may,
Amazing.
I'd like to emphasize two things, Stav.
Of course.
Okay. So I'd like to emphasize two things from what Hagai was saying. The first thing is that quantum key distribution is not something that will replace everything that's being done in the world. It will add another layer underneath everything, actually, which will add the level of security to be ultimate. And it will need to be combined together, okay? The second thing is that the maturity of the technology here now is getting to the position that it becomes relevant for the next few years. If you look at the market expectations for quantum key distribution systems, especially those, like Hagai mentioned, that are getting combined with classical communication, this is going to be a booming market, both in short distances and also in longer distances, both in fiber-based systems and in free space-based systems. So this is like a market that's about to explode, and it's a good opportunity to start getting into the market now.
Amazing. So we'll be moving to the Q&A. So I just remind everybody that you can ask questions. You have the bottom line there. You have Q&A. Just ask any question you want. So we already have a couple of questions. I'll take the first one to Tal. Tal, what breakthrough in quantum computing is needed to break cryptography in Bitcoin?
All right, so I'm not a big expert on Bitcoin, but I'll try to answer, and maybe Hagai will complete. So I think that the biggest challenge in quantum computing today is the fact that the quantum systems like atoms or ions or photons are extremely sensitive beings. The fact that they are so sensitive gives them the advantage in sensing. But in quantum computing, we would like to isolate them as much as we can from the world and make the cleanest calculation possible. So the biggest challenges technologically are enlarging the number of bits that we have and maintaining a very high level of precision in the operation or a very low amount of noise in the calculation. So far, if you look at your classical laptops, you have billions of bits there. Quantum computers will be able to do that in much, much less number of bits, but still, today, the most advanced quantum computers are at the level of 50 qubits, maybe 70 qubits or so. And there is a very big challenge to scale it up in number and maintain the performance. So I think that as Google stated a few months ago, they have reached the line that separates what you can do with a quantum computer that you can no longer do in a reasonable amount of time on a classical computer, even a high-performance computer. So we are on the brink of the quantum computers becoming practical, okay? Now it will need to be evaluated how many qubits we need in order to solve any specific algorithm. So the first algorithm that are expected to become practical and useful are optimization protocols. The farther away ones are ones that have complexity to do, for example, the quantum equivalent over the Fourier transform calculation, which is in the heart, for example, of code breaking, which is relevant there. And I think it's pretty early to say when exactly it will become available, if it's 5 years or 10 years or more. But the fact that was mentioned before by Hagai, that protecting the information already today is important, it shows you the relevance of dealing with the risks from quantum computers starting even today. So I hope this answers the question.
If I can add to the answer. So Bitcoin is using exactly the vulnerable algorithms we were mentioning before, like RSA and the elliptical curves. People are thinking about replacing these algorithms with what are called post-quantum algorithms, which are not quantum, but nevertheless, there's no certainty that they will withstand attacks by quantum computers. There's no certainty. The problem with specifically with Bitcoin that was in the question is that if you want to quantum protect Bitcoin, you need an extra ingredient of hardware called quantum memory, which is identical to having a quantum computer, almost identical. So these will be, and still quantum computers will be, at the beginning, will be huge machines that you will access through the cloud. So you'll not be able to have them on disk on key. So people are thinking about other ways to protect Bitcoin, but Bitcoin will be vulnerable to quantum computers. The answer is yes.
All right, so Hagai, we have a question here asking, is in what way is QuantLR doing something that is related to quantum cryptography? Is this the fact that you're using physics instead of mathematics?
Okay, so the answer is yes. I think the question was asked just before I spoke, so I actually answered it in my, but I will elaborate with a few more. We are sending exactly quantum single photons carrying quantum information from one point to the other, putting on top of that this procedure of quantum key distribution and generating the keys using this quantum information. So what we are doing is exactly the hardcore quantum cryptography. So the answer is yes.
Yeah, I will add to that because I'm talking to a lot of people that are not coming from within quantum physics or quantum technology. There is sometimes some vagueness in the terminology. So when people today are saying quantum communication or quantum cryptography or quantum key distribution, QKD, most of the time they're talking about the same thing. The vast majority of work in this field is in generating a secure secret key that is shared between parties that they can use that to encrypt all the information that they are using to communicate between each other. The reason that people are focusing on quantum key distribution or quantum key generation comes from the fact that the encryption keys are not a very big thing in terms of information. In order to do some computation, I need many, many steps, many logical operations. I need many, many bits. A key is of a finite length of, I don't know, 1,000 bits, 2,000 bits at most today, or maybe it will grow larger. And this is the easiest thing to start with instead of quantum encrypting the communication itself. This will come farther in the future where the technology will be able to ramp up the rate of generating and detecting these single photons. So all of these terminology of cryptography, communication, QKD, roughly today, it means, most of it means the same thing.
All right, Tal, I'm going to stay here with you for a second. What is the good estimate for when we would have a commercially viable quantum computer?
Okay, so as I said before, it really depends what you say as commercial viable. Okay, so we're on the brink of that stage today. We're already seeing huge investments in developing by companies that are making quantum computers like IBM, Google, Microsoft, and so on, and startups. But we also see more and more companies going into this field to actually solve their problems. Like I mentioned Volkswagen before, there is Daimler, the German car manufacturer, that are making optimization of the batteries for the electrical cars already. There are work on meteorological models to improve that. It's a big market. There are a lot of examples. The idea that was initiated by IBM, and now Microsoft has joined that, and Honeywell are joining that, and Google have said that they will join it very soon, of providing the quantum computing possibilities through the cloud, is it's a revolution in the way of thinking, because it will not, at the first step, not be like buying your personal computer. We will not need that. We'll have the hardware sitting somewhere in the cloud, and we will buy it as a service. And this is already starting to be involved. IBM has over 2 million users already today running the algorithms on the IBM platform. So this is really happening. And I think that the first commercial impact in the optimization market will be very soon. Most optimistic people say a year, maybe 2 years. Less optimistic people go toward the decade. It really depends on the kind of problem that you wish to solve. Also, there is a direction of research and development being shown more and more of doing hybrid problems. For example, the reason that companies like Lockheed Martin and Airbus has gone into quantum computing. For example, Lockheed Martin went into it for doing optimization on code writing or finding bugs in their code. They have millions and millions of code lines in the software for building an airplane, and they cannot risk the airplane falling from the sky because of a bug. And searching for these bugs is an optimization problem. So this is something that is already being used by these companies, and will have a very big impact already today with the current capabilities that we have right now. And also one last remark that I can say about this is that we all know very well from classical computers Moore's law, that says what is the density of transistors in a classical computer processor over time, getting multiplied every so often, and so on. So in quantum computing, it's very early on. There is something that we start to define as a quantum Moore's law. It's not the number of quantum bits. It's something that brings into account both the number of bits and also the quality of the bits. And we start to see a sort of an exponential Moore's law. Everybody today know what exponential trends are because of coronavirus, right? So we are starting to see this exponential rise in the capabilities of quantum computers. But on the other hand, we have to be very careful and say that we are at the start of this exponent. And it's a bit early to say how fast it will rise up.
Awesome. So I think we have time for one last question. I'm going to take the last question here. Hagai, how far is QuantLR from commercialization? And is there a market for your QKD yet?
So as I mentioned, we are just getting into the stage of R&D of working on our first product, which will be this module. So if we have our investment plans fulfilled, the plan is to have it working on our table within a year and a half. So we are talking about the end of this will be 2021, so the first quarter of 2022. But it will require compliance to standards, marketing, and so on. So I separate between ready to sell and sales, but the timeline is about a year and a half. What was the second part about the market?
Yep.
Okay, so we can discuss a few other companies that exist in this landscape, and the companies that do have products already have it installed in many places. There are many demo networks, but one maybe to mention is a company called Quantum Exchange. It's an American company based in New Jersey or New York, I think New Jersey, and they are buying equipment from QKD manufacturers. So it's mainly the biggest company, the largest company in the field is a Swiss company called ID Quantique. They are buying their equipment, but maybe also from other manufacturers, and installing it on standard communication lines and selling the quantum encryption as a service in the financial industry. So today they encrypt networks between New Jersey and New York, and now they are building a new network in the Boston area. So these are already installed systems, but as Tal mentioned, there are a few or many, depending how you count, but I'm aware of maybe 5 or 6 full research of the market research companies that published reports, and all of these reports are in the range. If you look at 2025 or 2024, they are all in the range, and the range is large because there is some uncertainty of, let's say, between 2 to 4 billion markets to 20 billion markets, and we are talking about 4 to 5 years. These are the estimation across the board of all these companies. So there are sales today. One of the problems in estimating the sale is that I do know from first-person conversations about installations of this hardware, but companies that install what is called quantum-proof hardware on their communication, they don't want to tell anyone that they do that. So I have a friend who was a Canadian, and he owns a company of consulting companies how to level up their security to the post-quantum era. And he said, we have dozens of customers, and I spoke with him a year ago, but he couldn't tell me even one name. We spoke about a month ago with an American company that is making this technology, and they are working only with government in the US, they cannot tell us about any installation because everything is secrecy. So we have to rely on this market research. That's it.
Okay, so we do have time for a quick additional question. Sorry.
I would just like to complement what Hagai was saying and look at it at what happens in the Israeli industry, and showing that this whole area is moving very fast. When we formed the national initiative, which was about 2 years ago, not long ago, we counted in Israel about 3 or 4 companies maximum in the core of quantum technology, not specifically only in quantum key distribution, but the whole thing, only 3 or 4 companies. Today, after less than 2 years, we're counting more than 20 companies only in Israel in this field. And this is similar also to the US and to Europe and other places. So things are moving very, very fast. both in how many people are involved and also in the demonstrations and the capabilities that are being put on the table. So the market is really growing. And I think this is something that needs to be taken into account when you think about how fast things will be implemented and used and so on. And also related to that, Hagai mentioned the market research that predicts what will happen in a few years, but we have already a few old national initiative documents. For example, the first one I think was the UK from a few years ago, and you could go back to that and look at the predictions that were written down in these reports, and they were predicting to 2020, to the present today. And you could see that these predictions are getting fulfilled, generally speaking. So it's not just predicting, it's also doing.
Okay, Tal, can you try to answer really quickly about the last question? Is there a relationship between 5G advantages and the maturity of quantum computing? Will they walk in parallel or interconnected?
Well, the standards for what people call 5Gs are not exactly formulated as of yet. So the standards are not set and the regulations are not set completely. Only the first deployment of 5G is defined. So I think it's a little early to say. I think that what the 5G infrastructure will help a lot is the way to have a lot of connections between people in a fast way. And so you will not need to have, a very special purpose processor somewhere, the ability to go through the cloud to actual users, the ability to have single photon devices working at the RF levels. These are things that we see in the future getting combined. So I think that there is a connection. The connection is getting stronger and stronger, but it's not formally defined right now. It's getting there.
Amazing. So I see that we have a lot of questions regarding QuantLR, but unfortunately we don't have time on this webinar. So just feel free to reply to this invitation of the event. Get to our crowd representative. We promise that QuantLR will be happy to answer any kind of question. I just want to thank everybody who participated. Thank you so much to Professor Hagai Eisenberg, and thank you so much to Dr. Tal David. You're amazing, and I think you really succeeded in explaining what it is quantum technology, which is super complicated, but I think it was understandable. So thank you very much for that and for your time, and thank you to everybody who participated. You're welcome to go back to our events.ourcrowd.com and see future events and participate. Thank you everybody for joining. We'll see you at our next event.